Hi everyone, this is another example with a ramp and a massless and frictionless pulley and two blocks as you see in the picture. The coefficients of friction between block M1, which is 5 kg, and the ramp are mu k equal to 0.25 and mu s equal to 0.3. We would like to find the magnitude and direction of the frictional forces on block 1 and the acceleration of the blocks for different values of mass M2, which is hanging from the massless string. First, look at the forces involved in this system. You see that M1G applies downward and the normal force is perpendicular to the ramp. Also, M2G applies to block 2 downward, which creates a tension in the string that applies to both blocks equally because the pulley is massless and frictionless. Now M1G has two components, one parallel to the ramp and one perpendicular to the ramp. The perpendicular component, which is M1G cosine theta, balances with the normal force and they cancel each other. Now M1G sine theta, which is 25 Newton, is much bigger than the 8 Newton tension force. Therefore, block 1 tends to move down the ramp. This creates a static friction force on block 1 directed up the ramp to prevent it from moving. However, even the maximum of static friction force, which is now 13 Newton, and the tension force together are not enough to stop block 1 from moving down the ramp. So block 1 starts moving down, and as soon as it starts moving, the friction force switches from static friction to kinetic friction. Now the two block system moves according to the values of kinetic friction force and the weights. And the tension force adjusts itself to keep the two blocks moving together with the same acceleration. This animation shows how the system behaves as the mass M2 is changed over a range of values. Okay, there seems to be a lot going on here. The friction force switches direction and also from kinetic to static depending on whether block 1 is moving or not. So let's slow down and look at this a bit more closely and quantitatively. Alright, let's start with a stationary system and M2 equal to 2.5 kg. Taking G as 10 meters per second squared for convenience, the weight of M2 is now 25 Newton, so the tension in the string is also 25 Newton. With M1 5 kg and theta 30 degrees, M1G sine theta is also 25 Newton down the ramp. Now if you look at the forces on block 1, they balance with each other, and as a result, block 1 does not tend to move. So there is no acceleration and no static friction is needed to keep block 1 stationary. Therefore, Fs becomes 0 and everything is in equilibrium. Now let's see what happens if we decrease the weight of M2 by 1 Newton. If we do that, the tension force on block 1 also decreases to 24 Newton. Now the forces on block 1 do not balance anymore and block 1 tends to move down the ramp. This is when the static friction kicks in to keep it from moving. So the static friction adjusts itself to exactly balance the forces on block 1. Therefore it changes to 1 Newton up the ramp. Now if we keep decreasing the weight of block 2 1 Newton at a time, the same sequence of events happen and the static friction keeps increasing to keep block 1 from moving down the ramp. Watch. But this can only continue until the static friction reaches its maximum value of 13 Newton, which is when M2 is equal to 1.2 kg. If we now decrease M2 to 1.1 kg, the tension force becomes 11 Newton and the static friction cannot keep block 1 stationary anymore and block 1 starts moving. As soon as block 1 starts moving down the ramp, the static friction changes to kinetic friction, that is mu k M1G cosine theta, which is 10.8 or about 11 Newton. Meanwhile, the tension in the string adjusts itself so that both blocks have the same acceleration. Notice that now block 2 is also accelerating upward and the tension in the string is not equal to its weight anymore and it is about 11.5 Newton. Now if we keep decreasing M2 even more, the story is going to be the same except that we get more acceleration. So let's reverse this process and start increasing M2. This decreases the acceleration and eventually stops the system. As soon as the system stops moving, tension in the string becomes exactly the same as the weight of block 2, and the kinetic friction switches back to static friction and tunes itself to keep block 2 at rest. Now watch the rest and enjoy. Now continue watching if you would like to see how we can decide whether the system starts moving or not, and how to find the force of friction and the acceleration of the system if the values of the masses m1 and m2 are given. This m1 5 kilogram, m2 is 2 kilogram, part A. Theta is 30 degrees, mu k and mu s are given. You want to see what is the acceleration, magnitude and direction of the blocks, and also force of friction, how much force of friction in which direction on M1. All right, so we need to analyze both of these, the two objects. First, we assume the system is not moving, and then see if there is enough force to start the system move. And for that, we need to find out for M1 how many forces are acting on it, how much is the force of friction, how much is the result of all other forces other than friction. So let's start with free-body diagram. We put the direction along the ramp as x direction, because if there's acceleration it will be this way, and y direction this way. How many forces? There is force of gravity, which is directly downward, and this angle theta will be the same as the angle of the ramp. And then normal force, which is perpendicular to the ramp, which is in y direction. And there is tension force. And there's a friction force. Friction, we don't know which direction it is, but we know that it is parallel to the ramp, so either positive direction of x or negative direction of x. If the system wants to go this way, the friction will be that way. If the system has tendency to go like up the ramp for M1, the friction will be down the ramp. Because we don't know yet, we cannot assume anything. Usually consider it positive. If you find it negative, it means that it is the other direction. All right. So this is our free body diagram. We can find the normal force, and by analyzing the y component of motion. And we know that there's no motion in y direction, so sum of Fy, which is equal to MAy, Ay will be 0, so this will be 0, right? So normal force is equal to M1 G cosine theta. So Fs max is equal to mu s M1 G cosine theta. How much is that?
Is it 12.73?
12.73
That's what I got.
Newton. So this is Fs max. Now we want to find the sum of all the x components along the ramp, which is x component, other than the friction itself. Sum of Fx disregarding friction. This is important. What are the forces? There's tension force, right? And M1G sine theta in negative direction, minus M1G sine theta. But what is the tension force? If the system is not moving, you look at M2, there's tension force upward and M2G downward. And this tension force is the same as this tension force, right? So T is M2 times G if the system is not moving. So sum of Fx is equal to m2g minus m1g sine theta.
Because negative 4.9.
Negative, that's
For the
if
whole
G,
thing.
Yeah, if g is 10, it will be like 20 minus sine theta is 1/2 minus 25, right? So 4.9, 4.9 Newton. Why is it negative? It means that this m1g sine theta is bigger than the weight. So the sum of these two has a magnitude of 4.9 Newton in the x direction. And you see that this is smaller than Fs max. So if you take the magnitude of this, which is magnitude of that, this is smaller than 12.7 Newton, which is Fs max. So since sum of all the x components is less than Fs max, then system will not move. Right? So the acceleration is 0, right? So acceleration is 0 in this case. So, and how much is the friction force? What is the magnitude and direction of the friction force?
It's going to be the static friction, right?
Static friction, how much is it? And which direction?
It's 12.7.
No, that is maximum, the static friction. Static friction is anywhere between 0 and this maximum. But how much is it? Remember, when we apply force, static friction just
extension.
it should be no, not equal tension. It should be equal to sum of these, right? So which is 4.9 Newton. If we calculate all the x components, became negative 4.9 Newton, and x direction was this way, means the sum of all the x component is down the ramp. Therefore, the friction will be up the ramp. So Fs is 4.9 Newton up the ramp.
Wait, how do you realize that it's 4.9 newtons up the ramp from that place? Yeah.
So some of all the x components became negative 4.9 Newton. And
Right.
became negative because we consider up the ramp as positive.
Okay.
That means that some of the x components are 4.9 Newton down the ramp, right? Therefore, because there's no acceleration,
I see.
the
Yeah.
static friction that just balances that.
Right.
So if there's total force is 4.9 Newton down the ramp, the friction will be 4.9 Newton up the ramp to balance that exactly.
Makes sense. And it's about trying to balance it exactly because A is 0.
A is 0, yes. Does that make sense?
Mm-hmm.
So this is how you decide. First, you find some of all the forces in the x direction that is parallel to the surface that has friction on that object, and then if that is more than Fs max, the system will move. If it is less than Fs max, the system will not move. But the friction is exactly opposite of that to make it not move. Right? All right, so now let's do part B. If M2 is 4 kilogram. If M2 is 4 kilogram, what changes? You see, when you calculate normal force, it just depends on M1 and theta. Those are not changing, right? US is not changing, right? So Fs max is the same. And then we say sum of Fx equal to T minus M1g sine theta, and T equals M2g. Now this will change, right? So the things from here on will change. Because we keep this here, and I delete all of this because this is the same as before. And now sum of Fx equal to M2g minus M1g sine theta. So how much is that?
14.7. That's what I got.
M2G, which is 40, about 40 minus that 25. Yeah, 14.7, that makes sense. 14.7. Right? Newton. And that is more than sum of Fx, disregarding friction, is more than the Fs max. Therefore, system will move. Right? Now, what is the acceleration? So how do we find acceleration? Yeah, we suspect that it's going up the ramp. The free body diagram looks like this. And with Fk if it is moving.
We're just expecting that it's going up the ramp because Fx is
positive.
positive.
Fx is positive, right?
Okay.
Fx is positive, so Fk will be opposing that. So the forces want to move this system up the ramp, so the friction is down the ramp. So the free body diagram becomes like this, right? And now we need to start over and calculate the acceleration using this. Will the tension stay the same? Do you think?
It's just, no, it's going to be 4 times G.
It will be 4 kilogram times G if the system is not moving. When the system is moving, it has acceleration, then T and mg are not the same. Right? So be careful. Every time apply Newton's law. Now that we know the system will move, let's find the acceleration. Free body diagram for M1 is the same. So again, we say the normal force will be the same. Now we analyze the x component. Once we have the normal force, now with x direction, it's the sum of Fx equal to max. Sum of Fx means T minus Fk, T minus Fk, and this is x component for mg, which is negative m1g sine theta. Is that clear what I'm doing? I'm writing all the x component. This is just the magnitude, this is negative magnitude, this is magnitude times sine theta, but with negative direction. So all the x components of forces on M1 equals to mass of M1 times acceleration. Right? But here, we know how to calculate Fk because it's normal force times the mu k. We know mg, m1g sine theta, but we don't know t and we don't know a. Right? So it's one equation for two unknowns. We keep it. For M2, we have free body diagram like this. And which direction is the acceleration of M2? If M1 is accelerating in the x direction, M2 will accelerate in the negative y direction, right? So the acceleration will be this way. The same magnitude, but downward. So when we write sum of Fy equal to may for M2, that will give us T minus M2G equal to M2 times y component of acceleration, which is negative A. Right? See, I'm following the math exactly. Now, you have another equation for A and T. If we multiply this by a negative sign, we get M2A, and then we can come back here. M2G, if you multiply by a negative sign, this equation becomes M2G minus T equals to M2A. And look at this equation and this equation. Now these are two equations with two unknowns. If we add the two equations, T will cancel out and we can solve for A. So M2G T cancels out, minus Fk minus m1g sine theta equals the other side is m2a plus m1a. I can factor a, say m1 plus m2 times a. And looking at this equation now, you can see that T was internal to this system. M2G is trying to push the system this way. Friction and M1G sine theta is trying to move the system the other way. And that net force is equal to total mass times acceleration. You could write this down from the beginning if you were careful enough. See this, M1G is pushing that way, not the T. M1G is pushing that way, Fk and mg sine theta is pushing this way, and that gives the total mass, the acceleration. So the acceleration is m2g times, Fk is mu times normal force minus m1g sine theta divided by m1 plus m2. Now we can put the numbers in. M2 times g, 39.2 minus mu k times n, 10.6, right? Minus m1g sine theta. Sine theta is 1/2, m1 is 5, this is 24.5, right? 24.5. So divide by the sum of the masses, 5 and 4. 5 plus 4 kilogram.
Oh, the top is 4.1, and then the whole
4.1.
thing is 0.46.
0.46, thank you. 0.46 meters per second squared. And you see, we found it positive. We considered the x-axis to be up the ramp, and we found acceleration positive, means that the acceleration will be up the ramp. And how much is the friction force? The friction force was this, right? Negative 10.6 means that it is 10.6 Newton down the ramp. Does that make sense? But if now F2 is 3 kilogram, suppose the system is not moving again, so the sum of Fx, disregarding the friction, will be m2g minus m1g sine theta. So m2 minus m1 sine theta times g. So that would be, let's take g to be 10. That's 30 minus, that's 50 times 1, it's 25. It's 5 Newton, about 5 Newton. That would be up the ramp, right? Because that's positive. That means that this is up the ramp, 5 Newton. And it is less than maximum static friction. Maximum static friction is normal force times the mu s, which is 0.3 times that, it's 12 point something. It's bigger than that, so sum of Fx is less than Fs max. Therefore, system will not move. But in this case, because sum of Fx is up the ramp, the friction will be down the ramp at exactly 5 Newton to keep the system from moving, because it can apply that much force, right? So Fs is equal to 5 Newton down the ramp.
I have a question.
Yes?
How is M2G in x-force?
A good question. M2G equals tension, and tension on M1 is up, right?
Gotcha.
And now, part D. What if M2 is 1? 1 kilogram. Then again, to write this, sum of Fx will be M2G minus M1G sine theta. So that would be 10 Newton minus 25 Newton will be negative 15 Newton, right? So sum of Fx will be negative 15 Newton. This has a magnitude that's greater than Fs max. So the system will move in which direction? In the negative x direction, right? Because the sum of fx is negative in the negative x direction. So if this has a magnitude of this is greater than Fs max. Fs max was 12 Newton, right? So system will move. And how much is the acceleration? m1g sine theta pushing that way, Fk is pushing up, and m2g is pushing the other way, equal to m1 plus m2 times acceleration. What is that? That's about 25 if g is 10. 25 Newton. What is Fk? Fk is normal force times mu k, which is 0.25. So that's 10.6, negative 10.6, negative m2g, which is 9.8 or 10, which is equal to m1 plus m2, 6a. You see, by writing that, I actually switched the x-axis because I wrote these as negative. If I keep the x-axis upward and write these in correct direction, this will be negative, this will be positive, and this will be positive. Then this will be negative 25, positive, positive. That is negative 4.4 divided by 6. So A becomes what? 0.733. That's meters per second squared. That's how much acceleration we get according to this x direction. Means that it is negative, means that it is down the ramp. Right? If you don't switch the direction, this is down the ramp, these are up the ramp, right? So you get that much acceleration. And how much is the friction force again? 10.6 up the ramp. Right?
When you say M1 and M2, like M1 plus M2, you do that because the system's moving and these two masses are connected?
Yeah, because you see, we have these two equations, right? If you write for individual ones, one t is in both of them.
Right.
If you add the two equations, it's like considering both of them as one system. T in this case is internal to the system, so it cancels out because the action-reaction is inside the system. Right? Then you see net force acting on the whole system is equal to the mass of the whole system times the acceleration.